So in this video, we're going to briefly introduce the analysis procedure for RLC series circuits. And if I asked you to guess what the resulting dynamics of these circuits would look like, you would probably tell me that since they still have two reactive components, namely an inductor and capacitor, that the governing equations will be second-order differential equations. And remember that those second-order differential equations are going to have the same solutions. So what we're probably going to see is analogous responses to what we saw for the RLC parallel circuit, with the only difference being that the governing parameters of those solutions, things like your damping factor along with your resonant frequency, are going to be different functions of the resistor, inductor, and capacitor values, because when we enforce our circuit laws in order to derive these equations, they're in a different configuration. So it's like the curves are the same, but the way that you determine alpha and omega naught is the formulas will be different. So if you think about how you would go about deriving the governing differential equation for a series circuit, probably not surprisingly, what you want to do is enforce Kirchhoff's voltage law across the loop. And of course, those three voltages will sum to zero. When you think about how this actually came about, of course, the voltage across the resistor is given by Ohm's law as a product of current and the resistance. In addition, when you think about the voltage across the capacitor, it's going to be related to the actual integral of the current, 1 over C, and you're integrating the current. And of course, the voltage across the inductor is L di dt. And then just like the case for the RLC parallel circuit, we're going to take another derivative to give this second order form. And the underlying sign conventions have been chosen in such a way that you have the sum of these three terms. But as the book mentions, and as I've mentioned a few times, and you'll see throughout the remainder of your electrical and computer engineering career, there's a lot of duality in the analysis of electrical phenomena. And the RLC circuit is, of course, the dual, RLC series circuit, I should say, is, of course, the dual of the RLC parallel circuit. So if you were to propose a candidate solution of exponential form and plug it in here and ignore the trivial option, where that exponential itself or the scaling constant is equal to zero, you're going to get a characteristic equation that governs the solution of this circuit. Namely, here is your characteristic equation, though. If you go back and compare it to the parallel circuit case, you'll notice that the appearance of the parameter values, namely L, R, and C, are in a little bit different place. So even though the general solution is the same, now your complex frequencies are going to be a little bit different. And what you should notice, I didn't talk about it too much, but in the complex frequencies for the parallel case, you saw kind of the analogy, you saw RC products happen quite a bit. And remember, that is your time constant for an RC circuit. Here you see things that look like your time constant for an RL circuit, as we talked about in the actual last chapter. So if we make a definition, notice that the resonant frequency remains the same. It's still 1 over the square root of LC. However, our damping factor now is going to be R over 2L. What we're going to see is we have these same three conditions depending upon the relationship between the damping factor and the resonant frequency. Namely, when the damping factor exceeds the resonant frequency, we have the overdamped solution. What we will find is our complex frequencies in this place are going to be two different real numbers. In the critical damped scenario, which is, of course, going to be really hard to get in practice, we have to add in that additional factor of t, since when these are the same numbers, they roll together, and you can't satisfy two initial conditions with only one unknown constant. And of course, for the underdamped case, you're going to have complex conjugate complex frequencies, and we will use Euler's identities in order to manipulate that into a form where we can see not only the exponential decay, but also the oscillating terms. So in terms of, if you were just to compare the source-free RLC circuits in the parallel and the series case, you notice that, again, the only thing that is changing are your formulas, particularly for the damping factor here. Alpha is different between the two, and just be careful and make sure that you identify which circuit you're analyzing, and make sure that you're applying the appropriate formulas, but the analysis procedure will work exactly the same. So because of that, we're not going to do any examples within this module, and we'll close the chapter by talking about the response of forced circuits.